My name is Akshar, and I'm going to be talking today about the mixing time of quantum Gibbs sampling for random sparse Hamiltonians. And this is joint work with Mehdi Soleimanifar from Caltech. So just for a brief outline about what my presentation will be about, I'm going to start out with an introduction to what quantum Gibbs sampling is. And then I'm going to discuss an algorithm for quantum Gibbs sampling, which uses this idea of Lombardian evolution. And then I'm going to talk about my research, which is about bounding the mixing time, or the algorithmic runtime, of this approach to perform Gibbs sampling. And then finally, I'm going to talk about some takeaways and future directions for this work. All right, so what is quantum Gibbs sampling? Well, one of the biggest areas of potential for quantum computing is the ability to characterize quantum systems. And so one task which we know that quantum computers are quite good at is simulating physical systems. So there are known results which show that quantum computers can simulate the dynamics of a physical system. But something that's less clear is the ability of quantum computers to evaluate static properties of a system. So for instance, one computational problem is preparing the ground state or estimating the ground state energy of a quantum system described by some Hamiltonian. And it's known that in the worst case, this problem is likely hard due to well-taken assumptions in complexity theory. But for generic quantum systems, you still might ask, when can we prepare the ground state or estimate the ground state energy or evaluate some other static properties of a quantum system? And so the question which I'll be thinking about in my talk is the ability of a quantum computer to prepare the Gibbs state of a system. That's the task of quantum Gibbs sampling. The Gibbs state of a Hamiltonian. Well, you have some Hamiltonian H with various eigenstates. The Gibbs state is a classical probability distribution over those eigenstates. And the classical distribution is essentially the Boltzmann distribution. So the probability of being in a given eigenstate that's indexed by I is proportional to e to the minus beta times the energy of that eigenstate. And here, beta inverse is the temperature that this Gibbs state corresponds to. So beta is the inverse temperature. And this distribution here shows the distribution over various energy levels for a specific choice of beta. And another way of expressing what the Gibbs state will look like is by evaluating e to the power of minus beta h, and then normalizing by the trace. So this is the quantum state that we're tasked with finding in order to perform quantum Gibbs sampling. So why should we be interested in the Gibbs state? Well, firstly, it's physically relevant. So Gibbs states arise in nature because they're the natural state of thermal equilibrium when a system thermalizes at a given temperature. And so just for that reason, they're physically relevant. Another reason why is because the Gibbs state at very low temperatures approaches the ground state of a quantum system. And so we know that at very low temperatures as a result, in the worst case, Gibbs sampling will be hard. On the other hand, as the temperature gets larger, the Gibbs state approaches the maximally mixed state, which is very easy to prepare. So we get this sort of parametrized problem of, as you vary the temperature, how hard is it to perform Gibbs sampling? And at some point in that spectrum, you'll reach a point where the problem goes from easy to hard. And finding that kind of transition is an interesting complexity theoretic problem. And then another reason why is we've seen that the universe is able to execute quantum dynamics that thermalize systems. And because quantum computers can also do simulation, there's a hope of being able to replicate those kind of dynamics and perform Gibbs sampling. And it's interesting to know when quantum computers, and likewise when the universe, is able to perform those kind of thermalizing processes. All right, so the algorithm we'll be thinking about today is an algorithm that uses Lombardian evolution to do Gibbs sampling. So let me explain what that means. So first, we can consider a general quantum system that's evolving with respect to some Hamiltonian H. And based on H, by Schrodinger's equation, we can say that the derivative of our state with respect to time is negative IH times the state itself. And so we're able to understand what the evolution of our system is over some period of time t by using this operator e to the negative IHG. And so this is how evolution happens in a closed quantum system. But instead, we can think of an open quantum system in which the system we are really interested in is suspended inside of a larger bath. And so this is the system marked by the dashed line, and we have the bath outside. And there are some kind of interactions between the system and the bath. And we'd like to understand how the state of the system evolves. And Limbladian evolution is a specific assumption on how that happens. And in particular, it's a similar first-order differential equation, but this time in terms of our quantum state expressed as a mixed state. So we say that the derivative with respect to time of our state rho is going to be this operator L, which is the Limbladian, evaluated on rho. So why are we using mixed states instead of pure states? Well, now our system is suspended in a bath. And that means that the system state could decohere over time. So it doesn't necessarily take pure states to pure states. So this is necessary for us to do. But just like we could do with Schrodinger's equation, by exponentiating the Limbladian, we can see what the state will be after some period of time t, given the initial state. Now, saying that our system's evolution is governed by a Limbladian is an assumption. It's a Markovian assumption. It's telling us that the dynamics of the system are determined only by its current state. We can figure out its derivative just by its current state. And that isn't something that's always necessarily true. For instance, you could imagine that over time, the state of the system could leak into the bath. So that's information from the system going into the bath. But it's possible for that information that leaked into the bath to return to the system. And if it did so, then we could no longer have this kind of Limbladian process, because then the dynamics of the system depend not only on its state, but also the state of the bath, since the bath state is coming back into the system. And so this is an assumption, which is that the dynamics of the system depend only on the system. And I'm calling it a Markovian assumption because classical Markov chains obey a similar assumption, namely that the evolution of that Markov chain depends only on its current state. And think of Limbladian evolution like the evolution of a quantum Markov chain. So in order for something to be a Limbladian, it needs to be true that when you exponentiate it, it's going to take quantum states to quantum states. So it should take PSD operators to PSD operators, and it should be trace preserving. And it turns out that the general expression for something that does that looks like this. So there's two parts to this expression. One is a coherent evolution, and the other is a dissipative evolution. So this coherent evolution is what appears in normal unitary dynamics. So this operator B here is Hermitian, and if that was the only term, the coherent evolution, it would correspond to Hamiltonian evolution with this operator B. So that's just a normal closed system evolution. Meanwhile, this dissipative evolution includes these Limblad operators, which you can think of as how the bath applies perturbations to your quantum system. So this is the dissipation that prevents our system's dynamics from being unitary and from being reversible. And so these are the parameters that need to be determined in order to give some kind of Limbladian evolution. So how are we going to be using this to our advantage? Well, in 2023, an algorithm was proposed by Chen, Castoriano, and Gillian, which essentially builds a Limbladian with two very useful properties. The first is that it's guaranteed to converge to the Gibbs state as time tends to infinity. So what that means precisely is that if I start with any given quantum state and I evolve the Limbladian for long enough, my system will converge to the Gibbs state. And the second property is that this Limbladian is efficiently simulable. So taken together, this means that I could create a Gibbs sampling algorithm that starts with an arbitrary quantum state and simply simulates the Limbladian. And eventually, I'll get to the Gibbs state, and then I can just return that as my output. There's one very important caveat, which is that I don't know how long it will take for my Limbladian to converge to the Gibbs state. So there's this important parameter called the mixing time, which is the amount of time it would take after which any starting state would get very close to the Gibbs state. If this mixing time is proven to be sufficiently small, then we already have an efficient Gibbs sampling algorithm. But if it's exponentially large, then this is not useful because we can't actually get the Gibbs state. And so in order to characterize the mixing time, there's one useful way to do it in terms of the spectrum of the Limbladian. So we can look at the spectrum of the Limbladian. It's always going to have one zero eigenvector, and that corresponds to the Gibbs state itself. We know that our Limbladian takes any state closer to the Gibbs state, and in particular, that means it leaves the Gibbs state stationary. So that translates to our Gibbs state being a zero eigenvector of the Limbladian. It turns out that every other eigenvalue is going to be strictly negative. And the distance between 0 and the next biggest negative eigenvalue is called the spectral gap. Now, as we exponentiate the Limbladian, all of the negative eigenvalues will decay. And if they've all decayed sufficiently, then any starting state will just get projected onto the Gibbs state. And so we can say that our spectral gap is approximately 1 over the mixing time. If you can get a lower bound on your spectral gap, that means that your algorithm can mix efficiently. And so in order to actually prove that the Gibbs sampling algorithm is efficient, we'll be trying to bound the spectral gap. to lower bound it in order to get an upper bound on the mixing time. All right, so what are the parameters of this algorithm? Well, it takes in two parameters, and the first one are these jump operators aj. So how does the algorithm use the jump operators? Well, it takes them and it decomposes them by frequency. So what that means is these jump operators, they can be written in the energy basis as a sum of these terms EI, EK. Now, decomposing by frequency means to collect all of the common terms which jump by the same energy. So for a given nu, which is going to be equal to the difference between these two energies, I'll collect all of the terms in aj which correspond to that jump. And so I can decompose it in this way, and the algorithm shows that you can reassemble these different parts in order to get our coherent term and our Lindblad operators for our evolution. And you can do that in such a way that this new Lindbladian has the properties that we want. It's efficient to simulate, and it converges to the Gibbs state. The second parameter is this energy precision sigma. You can think of that as the precision of this decomposition by frequency. So by Heisenberg's uncertainty principle, it's not possible to decompose by frequency perfectly, but you can do it up to some precision. As your precision gets smaller, so as sigma gets smaller and your precision gets better, the algorithm becomes more expensive, but it could perhaps have a better mixing time. It could be more performant. So what's the goal of my research? The goal is to develop some kind of mixing time bound for this algorithm. So find some class of quantum systems where you can establish a bound on the spectral gap, and in doing so, gain intuition for how to select the parameters of this algorithm in order to make it as performant as possible. And so this is the main theorem. So let's say we have a Hamiltonian H with the following property. There is a significant fraction of eigenvalues that are near the minimum eigenvalue. So 1 over poly n of the eigenvalues of our Hamiltonian H satisfy that their distance from the minimum energy, from the ground state energy, is on the order of the temperature of beta inverse. If this is the case, if a Hamiltonian satisfies this criterion, then it's efficient for a certain choice of our jump operators and our energy precision sigma. So what's the proof idea for this theorem? Well, what we do is consider what the expectation of the Lindbladian would be if we select one jump operator from a Haar random unitary distribution. So we choose essentially the most random jump operator we possibly can, a Haar random one, and we set the energy precision to be beta inverse, the temperature. Now it turns out that this Lindbladian, this expected Lindbladian, has a very nice property, which is that it decouples as the sum of two commuting evolutions. So one of them is this dephasing term, L dephasing. And what that does is it takes any quantum state and it sends it to a classical distribution over the eigenvectors of H. So what that means is that it could take something which is initially a superposition of the eigenstates and make it into a classical distribution. It's dephasing. The second evolution that we have, L classical, is a classical evolution on the eigenstates of our Hamiltonian that converges to the Gibbs distribution. So there's two things happening simultaneously. One of them is taking our quantum state and decohering it, so it's a classical distribution of eigenstates. And the second one is taking our distribution of eigenstates to the Boltzmann distribution. And the reason why that's so useful is because now we can bound the spectral gap using classical Markov chain techniques. This L classical is just a classical Markov chain, and L dephasing turns out to be simple to analyze. So because the distribution of jump operators was sufficiently random, when we took the expected Lindbladian over it, is very well structured. And that makes it easy to bound the spectral gap using classical techniques. So there's two obstacles to the approach as I've outlined it here. The first one is that we can't actually implement the expected Lindbladian. What we can do is sample a jump operator and implement the corresponding Lindbladian, but we can't necessarily implement what the expected Lindbladian is. The solution to this is to sample many jump operators from the same distribution. When you sample several jump operators that are all independently random unitaries, then you can prove that the Lindbladian you produce concentrates around the expected Lindbladian. It shares similar features. In particular, it has a similar spectral gap. So because the expected Lindbladian has a lower bound on its spectral gap, we also get a similar lower bound for this Lindbladian with several jump operators from that same Haar random distribution. The second obstacle is that a Haar random unitary is hard to implement. It's a prerequisite of our algorithm that the jump operators we propose are efficient to implement. The solution to this problem is that we can sample from a one design instead, a unitary one design, that matches two moments of the Haar random distribution. And it turns out that that matching in the moments of the distribution is sufficient for all the analysis of the algorithm to proceed. And there are efficiently implementable one designs. So we can choose our jump operators and sample them from a one design and still achieve the exact same proof. So what are the applications of this theorem? Well, it applies to sufficiently random, sparse Hamiltonians. So one example is you take a Hamiltonian, which is the sum of random Pauli operators. So there are results regarding the spectrum of this Hamiltonian which show that there's a non-negligible fraction of eigenvalues near the minimum. And that means that the theorem applies. Another example you could think of is if you select the Hamiltonian to be the adjacency matrix of a random log n regular graph. So by results in spectral graph theory, again, you get a well-behaved spectrum in the sense that many of the eigenvalues of our Hamiltonian are near the minimum eigenvalue. And likewise, you can use this approach to perform Gibbs sampling. So some takeaways. Why did this approach work? Well, you can think of systems with many low-energy eigenstates as easy. In the following sense, certain tasks which are often hard are easy for these Hamiltonians. For instance, it's pretty easy to estimate the ground state energy. How do you do it? You choose a random state, you measure in the eigenbasis, and you'll be able to measure the energy. And if you do this enough times, you'll get something which is close to the ground state energy, by assumption, because many of the eigenstates are low energy. And so, because these Hamiltonians are easy, related to this, we're able to choose generic jump operators, perturbations that don't really understand what's going on in the Hamiltonian, and that already suffices for an efficient Gibbs sampling algorithm. On the other hand, if the ground state energy was far from almost all of the remaining energies, then you would have to choose local jumps instead. It's no longer sufficient to choose Haar random unitaries or other highly non-local jump operators. Instead, you need to choose jump operators that are local, so they jump between nearby eigenstates. And here's a more precise statement. So in order to try and adapt the result for Haar random unitaries to more interesting Hamiltonians, you might decide to choose an interesting distribution of jump operators. So rather than sampling a random Haar random unitary, you could instead sample a random local jump operator instead. But the problem there is that if you choose a distribution of jump operators such that when you express that distribution in the energy basis, different entries of your matrix are correlated, then we've observed with several examples that that actually dampens the spectral gap. So you're sort of in between a rock and a hard place in the sense that you would like as generic a distribution of jump operators as possible to mitigate these correlations, but you must also choose jump operators that are local, so jump between nearby eigenstates, or the spectral gap will vanish anyways. And so, like I said, we would ideally have a distribution of jump operators that are local, but somehow avoid those correlations that end up dampening the spectral gap. And hopefully, if you're able to achieve this, then you can actually perform Gibbs sampling on more interesting Hamiltonians with non-trivial spectral properties. All right, so just a conclusion. This result demonstrates that the new Gibbs sampling algorithm that was proposed performs well on so-called easy Hamiltonians. And concrete examples demonstrate what's important in choosing the relevant parameters of the algorithm. But important future steps are constructing the correct technical machinery to prove that a choice of jump operators of local jumps would suffice to yield a fast algorithm for more non-trivial Hamiltonians, and build up a repository of results that show that this Gibbs sampling algorithm, which is general purpose, succeeds for interesting cases. All right, so just for some acknowledgements, I'd like to acknowledge my mentors, Mehdi and Anthony, as well as Professor John Preskill and the Preskill Group for hosting me, and my fellow undergraduate researchers last year. And I'd also like to thank the Caltech SURF program and my SURF donors for their support.
Thank you for the talk. And questions?
Thank you. Is there implications to finding ground state energy? Like, can you use your algorithm for to find ground energy when it's easy or when it's hard?
So this algorithm, this general purpose algorithm, certainly could do so. Our result only performs well in a context where, by assumption, there are many eigenstates near the ground state energy. So sort of by assumption, there are already easy algorithms for ground state energy estimation in this context. It's also worth mentioning that while Gibbs sampling for sufficiently low temperatures does produce energies near the ground state, it's sort of a more non-trivial way of doing it. Asking to produce the Gibbs state is sort of a high bar, and so you're asking for a structured state that includes low energy eigenstates. So the point of Gibbs sampling isn't necessarily to find ground states or ground state energies, but rather a more specific question of, can I produce this structured thermal state?
Do you know if this has any applications to finding new constructions for quantum expanders, for instance?
I'm not sure. So do you mean the Gibbs sampling algorithm or this mixing time result?
Well, both, right? The construction with the mixing time result.
I would say it's unlikely. Like, probably the right way to think about these results is there are ways of trying to generalize techniques that people have, a wide repository of techniques people have for bounding the mixing time of classical Markov chains to quantum Markov chains. And so far, people haven't found very good new quantum techniques that sort of differ from these classical ones. And so it's a more straightforward generalization in that sense. Although there's a lot of effort currently being taken into trying to find ways in which these quantum Markov chains are different and how to bound their efficiency.
Thanks.
Yes, thank you for the nice talk. So I was wondering, you say these Hamiltonians are easy, but is there a classically provably efficient algorithm for preparing these Gibbs states?
So it's sort of hard to answer a question like this. So these are like non-commuting Hamiltonians. So even the question of what it means to do Gibbs state preparation is difficult. That's a good question. So I'm not sure if there are classical algorithms to compute the partition function.
For example, for high temperature, right? We know that they're classically efficient because there's time and so on. So we'll just focus on this.
Right. It's a good question. So I do know that there are a lot of pitfalls in trying to find classical hardness problems out of sort of Gibbs sampling results like this one. Like, I've done some work in trying to find things that this Gibbs sampling algorithm can output that classical algorithms could not. And there are pitfalls. I'm not sure for this specific question if estimating the partition function would be easy or hard. But I do think it's very tricky to take these state preparation questions and easily distill classically hard problems. There can often be dequantization results or reasons why it actually isn't hard. So.
Hello. Does one need to know the eigenbasis of the Lindbladian beforehand?
No. So the eigenbasis of the Lindbladian does not need to be known. You just need a description for it. So in particular, the algorithm might start out with a block encoding of the Hamiltonian of interest. So block encoding is a primitive for expressing these operators. So you might want a block encoding of your Hamiltonian, of your jump operators, a specification of your temperature, and of the energy precision, and that's all.
Sorry, but block encode of the jump operators.
That's right.
I thought they were unitaries already.
Right. So they could be unitaries, but they actually do not have to be unitaries. Your jump operators can be arbitrary.
Okay.
Yeah.
Okay. Also, a different question then. How tight is the bound for like other cases that are not these Hamiltonians?
I'm sorry. How tight is
what the tightness of the bound that you
of the spectral gap bound that we gave?
Yes.
So let's see. So the bound on the expected Lindbladian is tight because that Lindbladian is so structurally simple that it's easy to characterize. It's a more tricky question on like if you sample several jump operators from the distribution as it concentrates. But if it's concentrated closely enough to the Lindbladian, then the bound will also be tight for the resulting Lindbladians.
Okay, thank you.
Thank you for the talk. So is there any dependence on initial state that can be computed, or like can then that be shown that for some particular state the mixing time is like even faster, or like if there is some fast forwarding that can be done?
Yeah, this is a great question. So it is certainly possible that the spectral gap is too pessimistic in the sense that the mixing time is roughly the inverse of the spectral gap, but like you said, there are certain starting states from which it is faster to get to the Gibbs state. So some kind of smart ansatz. That's certainly possible. Roughly speaking, you might hope that your initial state is somehow in the same phase as the Gibbs state, so that it's easier for your dynamics to bring your initial state to the Gibbs state. These kind of results are very hard, even classically. And so it's easier to start out with the simpler question of just characterizing the spectrum of the Lindbladian. But it's certainly possible that even if it seemed like the algorithm is poor, finding a good ansatz could solve that for you or improve its performance.
Thank you.
That's a very quick question.
That's right. I'm sorry, can you repeat that?
I mean, this is same as like classical mixing time. So if I could simulate classical in the sense that I could like sample the deep state.
It's true that this is closely inspired from the classical setting, but the dynamics you're simulating aren't necessarily dynamics a classical computer could do, because it's a quantum Markov chain.
Usually your mixing time depends on all the.
Right.
So here it's just dephasing it and getting it to the biggest part.
I see, right. Yes, in this context.
Like really quick, just in a previous conversation, you correctly noted that the jump operators are generally not unitary, right?
That's right.
So is it quite restrictive, the fact that you sample from random unitaries for the jump operators? Like,
Well, I would say in our setting, no, it wasn't restrictive. Let's see.
but like, are you, in some sense, are you missing out from a class of Lindbladians in that way? That's what I mean.
Right. So this specific technique is, right, like you could certainly choose other jump operators, but choosing unitary jump operators doesn't seem like an incredible limitation to me, because that doesn't necessarily mean the evolution you're undertaking is reversible. Like it's a distribution of different unitary operators, so there's still some decoherence that occurs.
Maybe we can discuss it after.
Sounds good.
But thanks.
Thank you so much for the talk.